Hi, I'm Chem's best friend. Please like and subscribe to my channel. And if you would like to know how to get in contact with me, the information is on the screen. Let's get started in today's lesson. Last time, in a previous video, we learned about Lewis dot structures. What are Lewis dot structures for? Well, they told us what atoms are bonded to what. They told us nicely on paper, a two-dimensional shape in a way, of what just atoms are bonded to each other. But they tell us nothing about the 3D shape of a molecule. So today we're going to learn about how to predict the three-dimensional shape of a molecule. Let's go to my screen. Well, let's look here. Why are we learning VSEPR? Look at these three molecules. They all have something in common. They have a central atom bonded with three other atoms. And yet, they have three different shapes. So, we have to learn how to predict the shape of a molecule. Before we do that, we need to learn what is an electron domain. So, here is the definition. A single bond will be classified as one electron domain. A double bond is one electron domain. Triple bond, one electron domain. Lone pair of electrons will be classified as one electron domain. And also, from time to time, you will see something a little different. A single electron, we will also treat it as one electron domain. And the thing about these electron domains is that they want to be as far away from each other as possible. So let's look here on the screen. If we have two electron domains. So here we will have two electron domains. Here is 3, 4, 5, 6. And two electron domains, they will be this linear shape, and they will want to be as far away from each other as possible. And you can see they will form a 180-degree angle. And here is nicely my two electron domains. Three electron domains is right here. It's going to be like a triangle, and they are all on the same plane. So this will be trigonal planar geometry, trigonal planar preliminary shape. When we get to four electron domains, they are no longer going to be on the same plane. Now we're jumping into a 3D realm. So we're going to have a tetrahedral geometry. So think of it as a tripod, and then a camera, and then a leg sticking up from a camera. And all the degree angles will be 109.5. So that's 4 tetrahedral. Then when we have 5 electron domains, what will it look like? Here I have this shape to make it a little easier for you to see. I have white atoms and green atoms. So the white atoms are all on the same plane. Do you see it? It's like trigonal planar, and yet there is something sticking straight up and straight down. So this one is our trigonal bipyramidal. It's like two pyramids. One pyramid is on top, one pyramid is on the bottom. Three-sided pyramid. So it's trigonal bipyramidal. And the degree angle between the white atoms, which are called equatorial spacing, on equatorial plane, is 120 degrees. Hopefully you can see this here. Here is my equatorial, and they are on the same plane, and there is 120 degrees between them. And the degree angle between the green and white, so the green are axial position, between every green and white atom is 90 degrees. So this I actually think is the hardest molecule shape to know, because you have two different degrees to know, to keep track of. So this is our trigonal bipyramidal. And then when we have six regions, here we will have 4 atoms on the same plane. They make a square, and then one sticking straight up, one sticking straight down, while they make like a 4-sided pyramid on top, just like the pyramid in Egypt. 4-sided pyramid on top, and they also make a 4-sided pyramid on the bottom. So altogether you have an 8-sided shape. And 8, what's a prefix for 8? More like a stop sign, octagon. So the shape of this molecule or electron domain geometry, we call it octahedral. So electron domains want to be as far away from each other as possible. And here are the rules. So what does VSEPR stand for? So VSEPR stands for valence shell electron pair repulsion. We're talking about valence electrons, right? The ones that are in the outermost shell, they come in pairs and they repel each other. So number one step is we have to learn how to draw a Lewis dot diagram for your molecule or polyatomic ion, and we did this in a previous video. Then we're going to count the number of electron domains. Remember, what's an electron domain? Any one of these things is considered one electron domain. We're going to treat each double, triple bond is counted as a single electron domain. And we will just count them. Then we're going to obtain our preliminary shape. I call it electron domain geometry. Then we're going to get the final molecular shape of a molecule. We're going to actually look what contains lone pair of electrons. Lone pair of electrons will be there. They take up space, but they cannot be seen. So here is a little cheat sheet. And the things which are highlighted the electron domain geometry, there is no lone pairs. So we said 2 electron domains right here will be a shape linear, 3 electron domains trigonal planar, 4 will be tetrahedral, 5 will be trigonal bipyramidal, 6 will be octahedral. And then the other things which are not highlighted are when you have lone pairs, and I will show you how to deal with this, but it would be nice to have this memorized. 7 electron domains is just not really going to see much, so we will not worry about this. So I think we're ready to practice. You ready? Let's go. So here we have pH 3. Now, pH 3, hopefully you watched the other video about Lewis dot structures where I mentioned for you there are some molecules it's just really nice to know, to memorize, so you can just swap some atoms like Lego blocks. And pH 3, in my mind, I'm going to draw like a little thought cloud. pH 3 seems like NH3 to me because phosphorus and nitrogen are in the same column of periodic table, so they have same number of valence electrons. So let's quickly do our Lewis dot structure. So we're going to put really fast. I'm jumping through the Lewis dot structures really fast right here. P is in the middle. I have 5 valence electrons plus 3 times 1, 8. And I'm going to jump them right in, put them right in. Here we go. Here is my Lewis dot structure. Now we're going to count our electron domains. Let's count. Here is, remember, each single bond is 1 electron domain. So here's 1, 2, 3, and each electron pair is 1 electron domain. I have 4 electron domains. Do you see it? All right. So I'm going to say I have 4 electron domains. Let's write this down. 4 electron domains. So my electron domain geometry is tetrahedral. Tetrahedral. And then we are right here. We have tetrahedral, 4 electron domains, but I have 1 lone pair. So 4 electron domains, I have 1 lone pair. I go right here. So my molecular geometry will be trigonal pyramidal. It will look like a tripod. So let me show you how to draw this. So the way I draw this is I'm going to put P here. Now I'm drawing electron domains. So I'm drawing, these are not bonded electrons. These are going to draw this one a little bit shaded. And the thicker line means it's closer to you. And then this one goes away right there. So now I'm going to put my lone pair right here, and my hydrogens I'm going to stick right here. There we go. And then my degree angles, let's think of degree angles. Well, it's tetrahedral is 109.5, but for tetrahedral we subtract minus 2.5 degrees for each lone pair. So 109.5 minus 2.5. So the degree angle between these will be 107 degrees. And this is also 107 degrees. And so now let's write my molecular geometry. It's going to look like a three-sided pyramid. So trigonal, pyramidal. And there we go. So yes, trigonal pyramidal, there we go. So that's our first molecule. We predicted the shape. So wasn't that bad, right? Let's keep going. So here we have BeCl2. Again, beryllium comes with 2 valence electrons. Really fast, let's do our 2 valence electrons plus 2 times 7. We have 16 valence electrons, and we're going to put in beryllium here, chlorine on each side, and then we're going to do 2 for each bond, and then octets from outside in. I used my 16, and is this done? Am I done with my Lewis dot structure? And remember from the previous video, yes, I'm done, because beryllium and boron can have less than 8. They are 2 very, very small central atoms, the 2 smallest central atoms you can have. So let's keep going with our VSEPR. Well, how many electron domains do I have? Let's look here. Here is 1 and 2. I have 2 electron domains, right? 2 electron domains. So I have 2 electron domains. So my electron domain geometry is linear. And my molecular geometry, where I have no lone pairs, is also linear. So if I draw it, I can draw beryllium here. Here is Cl. Here is this Cl. And I have how many degrees? The angle between is 180 degrees. All right. Next, CH2O. Okay. This one, let's think about our Lewis dot structure. We're going to stick in carbon in the middle. Hydrogens have to be on the outside, and also oxygen has to be on the outside. It's a very electronegative element. So carbon comes with 4 plus 2 times 1 plus 6. I'm going to add up. I have 12 valence electrons to deal with, 2 for each bond. And then I'm going to deal with octets from outside in. Hydrogen has only 2. So I used up all electrons. I look quickly, carbon doesn't have an octet, so I have to move these guys. I am moving right here to make a double bond. All right. So I'm going to quickly erase these, and I'm going to place them right here. Okay, so I'm done with my Lewis dot structure, and let's count our electron domains. Why is this molecule chosen? This is to make sure that you remember that this double bond is counted as 1 electron domain, right? So we have 1, 2, 3 electron domains. 3 electron domains and no lone pairs. So this molecule is not going to be 3D shaped the way it's drawn. Now I can draw any way I want on paper, right? Paper is just what's bonded to what. But now I have 3 electron domains. So my electron domain geometry is what's 3? Remember, trigonal, planar. And I'm drawing my picture of just what's bonded to what. I'm drawing my 3 electron domains. They want to be as far away from each other as possible. This is not a Lewis dot structure. Remember, this is not a Lewis dot structure. This is just 3 electron domains, and they will be 120 degrees apart. All of these angles will be 120 degrees. And my molecular geometry, because there's no lone pairs, is also the same name, molecular geometry, trigonal planar. There we go. Let's go. Few more. So H2O, are we ready? So we're going to quickly, I hope this is a molecule you have memorized. Oxygen here, here is my hydrogens, and oxygen comes with 6, hydrogen each one. So we have 8 total to deal with. 3, 4, 5, 6, 7, 8. Right there, I'm done. And I'm going to count. I have 1, 2, 3, 4. Do you see? 4 electron domains. Right? So we have 4 electron domains. So my electron domain geometry 4 is tetrahedral. Let's draw it. Here is my oxygen, and I'm drawing my 4 electron domains. 1, 2, 1 is going to be sticking out of the paper, coming right at us, and 1 will be behind it, going down, right? And I have to place my lone pair. So I'm going to stick my 1 lone pair on top right there, and I'm going to stick 1 below. And my 2 hydrogens, I have 1 right here, my hydrogen in here. So remember, it was 109.5, but we're subtracting 2.5 for each lone pair, and I have 2 lone pairs. So I need 109.5 minus 5. So this right here is 104.5 degrees. And what does it look like? Well, molecular geometry, I just have, it's bent. Now, I need to actually write which bend. It's 104.5 degrees bend. You can actually have 2 different bends. Let's go here. If I have 3 electron domains, just for a second, and if one of them was a lone pair, it will also be bent, but it will be bent with 120. So if you're taking an AP exam and you have a molecular geometry molecule that is a bent molecule, you actually have to put which degrees you're using. So here is bend 104, and if you really want to draw the end, the molecule, you can quickly draw it like this, and then just label your angle. Here it is, 104.5 degrees. It's not that bad, right? Not that bad. We're doing great. So SF2, why did we choose this? Why did I put this here? Well, hopefully you can see sulfur is in the same column as oxygen. Do you see it? And then we have a halogen, 2 fluorines. So they are going to, they usually like to form just one bond. Fluorine cannot just form one bond. So, given that, a little thought idea that this molecule better look like, can you recognize it? H2O, which we just did. Well, let's check it, right? So sulfur comes with 6 valence electrons plus 2 times 7, 20 valence electrons to work with. Let's do this here. Here is sulfur, fluorine, fluorine, 2 for each bond, octets from outside in, 16, 17, 18, 19, 20. Oh, wow. Let's look here. I have how many electron domains? 1, 2, 3, 4 electron domains. Yes, wow, this looks familiar, right? 4 electron domains. So my electron domain geometry, my preliminary shape is tetrahedral. And again, let's draw a picture. 1, 2, 3, 4, 4th electron domain. Let's draw our lone pairs where they go. I'm going to put 1 here, and it doesn't matter where you put your lone pairs. I just personally like to put them here. Here is this, and then my degree angle, same idea, is 104.5. So my molecular geometry, my final shape is bent, and it's the one bent with 104.5 degrees. How are you doing? Ready for one more? I think so. I think you are. Let's go here, O3. That's ozone. It's in the upper atmosphere, right? We need it to protect us from harmful gamma rays and cosmic rays. Okay, let's go. O3. So each oxygen comes with 6 valence electrons. We have 18 valence electrons to deal with. Let's put it all in the O here, 2 for each bond. Yes, octets from outside in. 16, 17, 18. Oh, wow, I don't have enough, right? So I need to either do this, move this one, or move this one. Either one or the other, not both. And when I have equal choice, do you remember that? That was that special resonance. Right, so we have to draw quickly 2 choices. One choice will be right here. And the second choice will be to do a double bond from the other end. So we will have a double bond here. So now, I wanted to do this molecule to show you how do you deal with resonance and VSEPR together. You know what? Choose one molecule now. You do not have to work with two, and we're going to choose one. So let's count how many electron domains we have. Here is 1, 2, 3. 3 electron domains. Yes, you see it? So let's write this down. We have our 3 electron domains. So electron domain geometry is, remember when it was 3? Trigonal, planar. And it's like this, 1, and then we have 3 electron domains, 1, 2, 3, and one of them has that lone pair, and then we have oxygen here and oxygen here. So trigonal planar, it was, remember, 120 degrees between every single one of them, but the lone pair you don't see. So then our final molecular geometry is bent. But it's a different bend that you already saw. So this is bent with 120 degrees. So here was bent with 104.5, here was bent with 120. So how did you do? Do you think you're ready to try a little bit harder ones? In the next video, we will do VSEPR, but we will deal with a little bit harder molecules, a little more difficult. So I hope you learned something new. Thank you for watching, and see you next time.